Hello and welcome everyone back to my another video. So this time I decided to implement my own reinforcement learning library. And as you might see, I already tested how it works with multiple environments that I trained to land a rocket on the moon. So basically that's already trained agent and you might see how it works. It works pretty nicely and it took me only 20 minutes to achieve this kind of results on pretty nice computer with GPU. So I want to introduce you this library that I'm just creating. You can of course access it on the GitHub and I can open it, and this is called RockRL, Reinforcement Learning Library. Right now this is on develop branch, but I'll release a version that you will be able to install it through the pip by simply pip install RockRL and you'll be good to go. Of course, I'll add a lot of examples how to use it, and right now I'm only focused on the PPO algorithm. That is one of the most popular ones, and I implemented this right now only on TensorFlow. And I plan to do this in Torch, but for simplicity reasons, I just made it with TensorFlow, and I believe with Torch it will be way easier to implement. You might see that it works pretty nicely, and this is only a lunar lander example. And in this video I want to introduce you with it and walk through the code, how it works, how you can train your own agent, and how to test it out. So I already running it, but you might see it lands perfectly. Well, it's not scoring the best right now because I trained it only for 20 minutes, but you might see that it is working. That's pretty nice. So let's open my code and let's analyze it a little bit. So you might see that there is my trained agent with lunar lander, actor, and critic. But let's go to the whole code. There is many examples in RockRL, TensorFlow examples, and PPO. There will be lunar lander, bipedal walker, and bipedal walker hardcore. That is really hard to train. But this tutorial is focused only on this example. This is a kind of discrete environment. This means that our agent output should be between 0 and 1 for different actions. And for this reason, I use a props and I use an argmax function. So right now I'm running this in multiple environments, but of course I can kill it and run in single environment. So there is my single script. It's pretty simple, and I can move it on. Oh, it's training. So test. Here is the test. So let's look at the test first. I must mention that this will work only with latest Gymnasium and library, and I tested this with 0.29.1. I believe it will work with higher versions, so I can put like these, and it will be just perfect. And I'll release a RockRL library 0.04 version. It's not released yet, but I will release it and you will be able to install it through pip. So basically, right now I'm recording this tutorial on TensorFlow. And if you are familiar with TensorFlow, you already know that it's really hard to install TensorFlow higher than 2.10 with GPU support. So I'm testing this on Windows with this kind of version, but on Linux I tested with higher versions. It works pretty nice, and you might move with it. So these are the requirements what you might need to work with this. And if I go to my test code, let's walk through this. So what I do is pretty simple. I import the models. I load the Keras trained model for this kind of lunar lander environment. This is render. This means that I want to display it as human with how the rocket lands. And Then I simply call the reset environment and I use a predict on the state, on the first state. And I use argmax to get my first action, and I use a step function and I render the environment. And I just collect the scores through all the steps. And simply then I restart it. So if I'll run it, it should appear here, my environment. Let's look at it. You might see that it's here, it works, it lands, and etc. The same works with multiple environments, but to work with multiple environments, I implemented a little more stuff to make it easier for us, either for testing or either for training. So I will use this, I'm using the same model for multiple environments. So let's kill this right now and go to my multiple environments. So right now, here's my multiple environments. And here I have few more objects that I implemented. This means that I am using vectorized environment. So this kind of very nice object that I can use to run this on multiprocessing. So this means, for example, I spawn 4 different environments and I predict the state for all of these 4 environments. And what I do, I simply collect this information with multiprocessing and I use Pine for communication. So that's great. And here I'm memory manager, and this is kind of special also object that it's pretty small, but it handles the memory object. And this memory object is pretty simple. It simply collects all the states from our environment step function. So state, actions, rewards, predictions, terminated, truncated, and etc. And next states, info, dictionaries, and etc. And this means that I append this information into my memory. And when I use a get, I simply restart this memory. And that's pretty amazing how simple it is. So let's go here and let's analyze a little bit this code. So what I do here is that I call the environment reset, the same as I did for one environment. I do this for 4 environments, and this will restart all 4 environments for me. And then I use a predict on these states. This is 4 states from all 4 environments, and I receive these probabilities. And these are the actions. I collect the argmax function from on these probs, and I receive the actions. And I call the step on it. And that's it. And then what I do, I check whether my environment achieved the termination state. This means that if it was terminated or truncated, and I need to simply to know which environment got this state. And for this environment, I reset the environment and memory specifically. And as you might see, when I reset this environment that I use to identify by index, I receive a state and I update the states with this environment. And that's pretty simple how it works. Okay, you must see that's pretty simple inside, but this is a faster way to test my lunar lander, because you saw that it takes a little time to land it, and when I use 4 environments, it's way easier. And usually I use 48 environments, so you might believe that it takes several seconds to, for example, test 100 epochs, because we can run the predictions in batch, so there is no any issues with that. So, but I believe you are mostly interested in training code, how it works with this PPO. So I implemented also 2 environments. So this is one simple environment that I'm not using multiple agents for this one, and we'll come to this a little later. So what I do here, I import mean average, memory, and PPO agent. This PPO agent is my object that handles all the logic behind the PPO algorithm. And you might see, oh, I need to install this library, but okay, I'm not going to train it right now. Or I can, I don't know. Let's see if I have it here. No, I don't have. Maybe here. Yeah, I do have here. So let's install this. Pip install. Okay, let's go back to my single. And here I simply define my actor and critic models. That's what happens behind this PPO agent. We must have two different models, and I use the same architecture for both of them, but you might use different ones if you want. And most crucial part is the output. So dense layer output, and I use softmax for actor and simple dense with one neuron at the end or in critic. And then, the same as before, I simply define my environment. I create this environment. I define actor, and I give it an actor and critic models that is using while training. And I define the optimizer, the batch size of the training code. This is KL divergence. Well, that's also a story for different tutorial because it's more advanced stuff, but it stabilizes training. And I use C2. What is C2? So we can find everything here. C2 is entropy coefficient and it's default to 0.01, but I use 0.1 and I can add writer commands to TensorBoard and etc. So what I do next is I define memory for one environment that I'm using here, and I define mean average. I use this mean average to average mean score from 100 environments. I think, oh no, it's from 50 environments. And when I achieve the best score of the mean, I save the model. And next time when I get better mean score, it means my mean agent is improving, so I can also save. So that's the main logic. And why I mentioned that I recommend to use Gymnasium with the latest version, because in the old version there was only 4 returning states, and in the newest version is 5, and we don't have done. But that done is usually terminated and truncated and used orbit before done. And terminated means simply, for example, that our lander crashed, and truncated means that, for example, our lander achieved maximum environment steps. And at this step, we want to also stop it and not to continue training it. So each iteration, I append this into the memory, and at each step, I check whether it was end of this environment. And when we achieve the end, I use a train on this memory. So I train the agent on this collected memory, and then I reset the state back to original what it was before. And then we simply collect all this information. And you might see why I'm not, for example, resetting the memory each step. Well, because it's implemented into the memory. When we train the agent, when it gets everything from the memory, it by default resets it on the next append. So this is here. We check the state, whether we need to reset it or not. And when we get a reset, we set it as true, and that's it. And I'm not sure if you are interested in seeing the PPO training code, because it's pretty complex, but I made it to work pretty nicely, and you might see it. I trained the agent that works pretty nicely. So let's go back to this single step. And if I can cover this PPO agent code a little bit quickly, and you might see that it has action space, it's discrete or continuous, and we need to set it before training our agent. And I will cover the continuous environment in another tutorial that I tested on bipedal walker, and also I trained it pretty quickly and everything works pretty nicely. and that's it. And there's a lot of parameters that we might set, but I'm not going to cover it right now. I try to update the documentation so you might read it, understand by itself. So that's it, and let's walk through the crucial parts of this PPO. So we are saving the configurations when we want to, for example, a training model, we want to know what configurations and hyperparameters we use to train a PPO. That's pretty crucial for reinforcement learning. So that's very useful function. Then I save the models, I save actor and critic. And here is my critic loss that I use, and there is my actor loss also will be there. So there is a lot of log prop distribution, continuous and discrete functions that I used. And here's my actor loss. And we use a different kind of computation stuff and different logic, whether we use a discrete environment and continuous. And yeah, we calculate the advantage loss, and we calculate the approximate KL divergence. And of course, we turn sigma and etc. And here is an action function that we use on every step, and etc. It's nothing magical. I calculate advantage reward with following function. I tried to implement this in TensorFlow, but there was no improvement using it, so I decided simply to use a NumPy. It's a little easier with it. And I use a predict chunks. That's another function that I use, and it's really useful when we are training these agents. So when I'm running the environment, we don't need to run a critic prediction on each step, and I am able to run this prediction only on full batch of my agent. I can reduce learning rate with this custom function, log writer, custom logger, train step wrapper, and etc. There's a lot of implementations, and main logic happens here within train step, but who calls it? This following train function. So on each iteration, we call this train, and we are, as you might see, you must feed the memory object to this, and from this memory object we receive the states, actions, rewards, everything we need, and I calculate the GAS, discounted rewards and advantages. So as you might see here, I use a predict chunks on a critic model, as you might see. And why I use a predict chunks? Because sometimes we have environments that, for example, last for 10,000 episodes. And if we'll try to predict with these all 10,000 episodes at once, we might face some kind of issues with GPU memory. So it's way faster and easier to predict simply on some kind of batch. So this means we predict on batch. And that's it. I update the tensor board with following function, and I call this train step with states, advantages, all probabilities, actions, and targets, and that's it. If I go to my train step, there is a lot of different things. So whether I want to use shuffle or do not, and I simply use gradient tape to do the back propagation of my neural networks. And then as a result, I return a dictionary of a loss, actor loss, critic loss, entropy, approx KL div, sigma, and etc. Basically everything we are interested while training a PPO agent. And that's it. I just made a quick review. If you want to get deeper into it, you might test this out. You can check my code on GitHub. It's open source, and you might find everything in the description below. So, okay, I trained this lunar lander, but I believe it doesn't tell you anything if I tell you that I trained it. So we have this TensorBoard logs that we can check it out right now. So I opened my TensorBoard. I will have it right now here, and we might look at the logs. And yeah, usually when we are training our PPO agent, it doesn't tell us a lot of information what this means, but simply the goal is to make actor loss close to 0. Critical loss is also, we are trying to make it close to 0. And then we have some kind of entropy and KL divergence. And entropy is kind of randomness, what comes from the PPO agents. KL divergence is might tell us when our agent is overfitting or not, and simply it's a good metric when we use a high learning rate or etc., and we might see that it skyrockets, there is a huge spike. This means something is wrong with our hyperparameters and we need to adjust them. So this is one of the nicest metrics I found. Then there is combined loss with actor and critical loss. There's a learning rate that was stable for this kind of stuff. And there you might see that I trained my agent for 10,000 episodes and how fast it was improving. So it took only 1,000 steps to achieve this kind of high scores, and it continued training on these high scores. And I used mean average from these scores to find which part achieved the best average rewards for me. There is of course sigma, and sigma represents the randomness of our actions from our agent. And usually while training it, it should decrease to 0, but you might see it's not. So this means that maybe I used too high learning rate or etc. So this means I might adjust some hyperparameters to get a better results. But right now I'm really satisfied with my results, and you might see that it took me only 17 minutes to train this kind of agent. I used 48, I don't know, I think I used 48 agents. Let's see if I have it here, but no, it's not saved here. Okay, but it doesn't matter how many agents you use, but usually when more agents we use, faster it will train. And that's it about it. And you might see it works, and you might test this with other different environments. I used lunar lander because it's not that complicated and not too simple. So and I was able to quickly train this. And this was one of the best environments for me to test whether my PPO and algorithm works. And also then I tested this with continuous environment, but that's for next time. So that's it about this tutorial. We can run this code with multiple environments, and you might check it out again how nice it works. So let's open it. It gives me some information terminal before it loads, and we might see that it works just nice. So that's it, what I wanted to show you. If you want to test this out, my library, okay, it's open source on GitHub, and you might use PyPy to install it. It's up to you. If you find any improvements to this library, I'm open to merge your changes or implement your suggestions, etc. So thank you again for watching. It was a pleasure to show you what I'm working on, and I simply want to implement this reinforcement learning agent so I can work on it, improve it, add more algorithms in the future if I would like to. And I would say that it works better than stable baselines, at least for me, because on other environments, it was easier for me to train an agent than using stable baselines. And of course, in stable baselines, it's pretty complicated to change the architecture of our models that we want to test for training and etc. So I implemented everything from scratch and everything works for me. And of course, while implementing, I learned a lot of stuff. That's my goal. And that's it about this tutorial. I really appreciate if you watch until the end. If you smash the like button, I would thank you. And of course, don't forget to subscribe to my YouTube channel. This would help me a lot. And for now, that's it. We'll see you in the next video tutorial. Thank you again for watching and see you next time. Bye, my friends.